Now, after having introduced the generalizations, the abstractions of inner product spaces and normed spaces, we were just at the brink of introducing the generalized distance, the notion of a metric. So we'll start with that. That's 1.5. It's about metric spaces. We will proceed as in the preceding two cases. We had the so-called properties of the usual distance, the proposition about that, a list of properties. We will now take those properties as the defining axioms, the defining conditions of a metric space, of a metric. But again, if you go back and look at the list of the properties of the usual distance, although we had started with some real vector space, then an inner product on that, we induced a norm using the inner product, and we defined the usual distance using the norm. But the conditions, none of the four conditions listed there, they do not require any real vector space structure. So just if you start with a non-empty set, say cap A, define a function on A cross A, that is to pairs of members of that set, if you assign to that a real number, and if that function satisfies all the properties, that will be a metric. So we'll start with a non-empty set. Let A be a non-empty set. Now, a function, let's denote the function by M. So this will be on A cross A. It takes a pair of members of cap A and associates with that a real number, which is to be interpreted as the generalized distance between the 2 points in question. Is called a metric if the following conditions are satisfied. So M1, well, that was the distance between 2 points, xy, that was larger than or equal to 0. So we'll have that here as well. For all xy in A, mxy, that's larger than or equal to 0. The second condition dealt with when this mxy was 0. Well, that was a biconditional. If x and y are the same, they're equal, then the distance is 0. And if that distance is 0, that should in turn imply that x and y cannot be distinct. That is, for all xy in cap A, mxy equal to 0, if and only if, so this is an arrow in both directions. Thirdly, the third condition said the distance from x to y and that from y to x, they're the same. Here we'll have the same. For all xy in A, mxy and myx, they're supposed to be the same. And finally, we had the triangle inequality. That is, if I have 3 points in the space, then there are two possibilities. I can find the generalized distance from x to z, but I can also go from x to z via y, first from x to y, then from y to z. The latter, that sum should be larger than or equal to the former. So mxz, that is supposed to be less than or equal to mxy plus myz. Now, when M is a metric on A, we refer to the pair A and M as a metric space. Now let's see some examples. Now firstly, we'll have, let's first note down the following proposition. R and D, where D is the usual distance in Rn, is a metric space. We have already proven this. The proposition, the proof of the proposition concerning the usual properties of the distance in Rn is just a proof of this. Proof already done. Now let's start with a simple example. Let's take our set equal to R. Of course, you can define plenty of different metrics on one and the same set. Well, on R we have the usual metric. We'll refer to the usual distance as the usual metric henceforth, but we can define others as well. Define M, well, let me give a number to that, M1 on R cross R into R by taking mxy as the minimum of the absolute value of x minus y and 1 at each xy in R cross R. Now, in fact, the absolute value of x minus y, well, that's just the norm of x minus y in R, because in one dimension, the norm, the usual norm, that reduces to the absolute value. Well, here this tells, now we're not interested in keeping track of, well, when the usual distance between 2 points is larger than 1, we just write 1 and, well, we interpret that it's large. Okay? Well, we do not know whether this is a metric so far, but let's see, it will turn a metric. Well, then let's go through the properties, but I will not write M1, M2, M3. I will just go inverse But if you're in an exam or in a homework, you're supposed to write that. Now, firstly, take any xy. Will this quantity be larger than or equal to 0? Well, it's the minimum of two numbers, both of which are non-negative. So the minimum will be one of them and non-negative as well. So that's M1. That's done. Now, this has two parts. First, assume x is equal to y. Well, if x and y are equal, this will become 0. The minimum of 0 and 1, that will be 0. So m1xy, when x is equal to y, that will be 0. Let's go the other way around. Suppose m1xy is equal to 0. Well, that means that this minimum is 0. But since 1 is not equal to 0, the minimum then must be the absolute value of x minus y. But if the absolute value of x minus y is 0, so also is x minus y, which means that x is equal to y. So M2, that's also satisfied. As for M3, well, if you consider xy and yx, then this becomes, in one case, this, the absolute value of x minus y. In the other case, the absolute value of y minus x, but they're equal. So you're taking the minimum. M3 is also satisfied. Now let's see M4. Now for M4, one possibility is, well, you can consider different combinations, what can happen, because you'll take x, y, and z. You'll consider mxz, that might be 1 or the absolute value of x minus z, and that will pertain to mxy and myz as well. But it's good to find shortcuts. So one possible shortcut is the following. It is based on the following observation. We wish to show that mxz or m1xz is less than or equal to m1xy plus m1yz. Now, by this definition, well, actually, m1xy, that will be larger than or equal to both of these, because it's the minimum. It will be less than or equal to both of these because it's the minimum of them. So we can use that, and, well, we can take the following two cases. Case 1, m1 xy equal to 1, or m1 yz equal to 1. Now, what do we have? Now we wish to show that m1 xz is less than or equal to the sum of these. But m1 xz, well, will be less than or equal to this and this, but in particular this. So this is less than or equal to 1. It will be the minimum of two numbers, one of which is 1, so it cannot be larger than 1. But this will be less than or equal to, in this case, m1 xy plus m1 yz. Why is that the case? Well, at least one of them is 1, and the other is larger than or equal to 0. Since one of the above terms is larger than or equal to 1, while the other is larger than or equal to 0. So for this case, we have established the triangle inequality. Case 2, the negation of this. But the negation of this is that m1 xy, that's different than 1, and m1 yz, that's different than 1. Now, what does that mean? Well, m1 xy, that was supposed to be equal to the smaller of these two. If it's not 1, it must be this. Likewise for m1 yz. m1 xy, that's equal to the absolute value of x minus y, and m1 yz, that will be equal to the absolute value of y minus z. Now we have, let's start with m1 xz. We wish to show that it's less than or equal to this sum in this case as well. But as we have noted, m1 xz is less than or equal to the absolute value of x minus z and 1, less than or equal to both. So in particular, it's less than or equal to x minus z. Well, if x minus z is larger than 1, this will be equal to 1, but it will again be less than or equal to this. Now let's apply the famous trick here. X minus y plus y minus z. We add a 0 to this, so the value does not change. So we have here equality. But since this is the usual norm in R1 and satisfies the triangle inequality, we have this, but we have noted in this case these two quantities are equal to m1 xy plus m1 yz. So m1 is a metric on R. Now let's remember, well, the title of this chapter was Elementary Topological Properties of Euclidean Spaces. We still do not know what the topological structure is formally, but our aim was to formalize what it means for a point to be arbitrarily close to a set. So we're interested in arbitrarily small distances. If we are to use the notion of a distance or the notion of the generalization of a distance, the metric, in formalizing some point being arbitrarily close to a given set, well, that means, well, so this is, in some primitive tribes, you have 1, 2, 3, and a lot, much. Well, after that, it's much. So this is like thinking in those terms. Well, if the usual distance between x and y is less than or equal to 1, you're interested in the actual value of that. If it's larger than 1, well, then you say, well, that's large, and then you represent largeness by 1 in here, and we'll see that that's meaningful in the context of metric spaces. Now, the second example, now let's take A equal to Rn and define M2 on A cross A into R by M2xy equal to. Now the usual distance that was defined as follows we take each component I, we form xi minus yi, we square that, then we sum those squares over all components and then take the square root. Well, instead of that, let's try the following. Again, let's go component-wise. We squared them in the usual distance because we wish the sum to be something non-negative. But let's take the absolute value of that. Well, square them and then take the square root of the sum. Well, let's just not square them. We made them non-negative via taking the absolute value. But let's just take this sum and declare that to be the definition of this metric. Well, we still do not know whether it's symmetric or not, but let's check. Is M1 satisfied? Well, take any xy, any two n vectors. Well, each of these quantities is non-negative. The sum of non-negative quantities is non-negative. So M1 is satisfied. For M2, if x and y are the same, so that means all the components, corresponding components are the same. For each I from 1 to n, xi and yi are the same. So this becomes 0 for each I. So this is the sum of n zeros, which is 0. So one direction that holds. Okay. Now conversely, assume that m2xy is equal to 0. Then this sum of n non-negative numbers is equal to 0, but then all the terms individually must be equal to 0, for otherwise the sum would be positive. But if each term is 0, then this means for each I, xi and yi are the same. Thus the two vectors are the same, so M2, that's also satisfied. For M3, well, xy and yx here, well, then you'll have here in one case this, but in the case of yx, the absolute value of yi minus xi, but the two absolute values are the same because the expression is multiplied by 1. M3 as well. Now let's check M4. Let x, y, z be any three members in Rn. Now M2 of xz, well, by definition, this will be the sum of the absolute values of the difference of the components. But then what? Now, for each of these terms, xi and zi, they're real numbers. This is the usual norm. So we have this satisfied. This is xi minus yi plus yi minus zi. I equal to 1 to n. But this is just the sum of the absolute value of xi minus yi, I from 1 to n, plus the sum of I from 1 to n, yi minus zi. But this is just m2 xy, and this is just m2 yz. So component-wise, triangle inequality being satisfied component-wise, automatically it's inherited by the entire metric itself in this case. So M4 is satisfied. Hence, M2 is a metric. Well, M2 is a metric which seems to be closely related to the usual distance. It's different than that as a function. But we'll see they're equivalent in a sense, not today, but on Thursday. But this much, well, we said we don't need the real vector space structure of the underlying set to define a metric, but these two examples are on Euclidean spaces. So let's give an example, at least one example, where the underlying set has no structure at all. Example 3. So we'll take A to be just a non-empty set. Well, if A is a singleton, has just one member, there is just one trivial metric because the Cartesian product of that set with itself, that's just XX, and no matter what metric you define, MXX, that must be 0. But if it has at least two members, then we can ask, what is a minimal range in R for this function to be able to be a metric? Well, this must contain 0 because A has at least one member X, MXX is 0. But what else? Well, if it has two different members, at least, X and Y, different than each other, then MXY must be larger than 0. So the range of this function has to contain, in that case, at least one positive number as well. Can we do it with exactly one positive number? Well, if you wish to take a representative positive number, well, most of the time you take 1. Let's take 1 as well. Well, if the range of this being 0 and 1, consisting of 0 and 1, if that allows this to be metric, then the metric will be automatically determined. Well, take xy. If x is equal to y, then mxy is 0. If they're different, well, then there's only one possibility, mxy will be 1. Now, let's define it like that. Define this by mxy equal to 0 if x is equal to y, 1 if x is different. If this works, well, this is in fact an exaggeration of the approach of some of the primitive tribes. Well, if they're the same, no distance. If they're different, there is a distance. So it's just a binary logic at each xy in A cross A. Well, this is 0 and 1. mxy is either 0 or 1, thus larger than or equal to 0. Well, if xy is 0, by definition, this is 0. If mxy, if that's equal to 0, then x and y have to be the same. Otherwise, they take on the value 1. So M2 is satisfied. Well, mxy and yx, x is equal to y if and only if y is equal to x, so that's satisfied as well. So M1 to M3, they're satisfied. Let's check M4. So let x, y, z be points in A. Well, again, we can, in a sense, imitate what we did in case 1. mxy or myz, if at least one of them is 1, since mxz will be less than or equal to 1, we'll get the conclusion. So case 1, mxy equal to 1 or myz equal to 1. Now, mxz, that will definitely be less than or equal to 1, but this will be the sum of two numbers, at least one of which is 1 and the other is larger than or equal to 0. So that will be satisfied. Case 2, mxy different than 1 and myz different than 1. That's the negation of this. That is mxy. Well, if it's different than 1, it must be 0. If this is different than 1, it must be 0. That is, x is equal to y, and y is equal to z by m2, which we have already shown. So, x is actually equal to z. Thus, mxz, that is equal to 0, but that's equal to mxy plus myz. Well, so I can write this also as less than or equal to. So, M is a metric on A referred to as the discrete metric on A. Now, A is any non-empty set, and well, we have now a metric, the so-called discrete metric, which applies to any set whatsoever. Now, fine, this is a genuine generalization of distance. Well, because here the question in general, well, whether a metric can be induced by some norm, well, we know that that's not the case because the set we start with need not have a real vector space structure, so there is no norm on that, thus there is no norm which induces the metric. But let us now confine ourselves to real vector spaces, and well, let's ask the following. Given a metric M on a real vector space, does there always exist a norm on V, on the real vector space, which induces this metric? So, for the sake of completeness, let me start by noting down the definition of this inducement. We have done that for the previous generalizations, for the previous cases, but not for this. In fact, we have here the following proposition as well, which has again already been proven when we considered the usual distance properties. Now, so proposition let V be a normed space. So it is a real vector space structure plus a norm. Define M on V cross V into R by M of xy equal to the norm of x minus y, which is the norm given here at each xy in V cross V. Now we already know that this is a metric. Well, we did that when we considered the norm properties, well, the distance properties being deduced from a norm. Now, M is a metric on V referred to as the metric induced by this norm. Proof already done. Where we showed that the metric properties follow from the norm properties in this case. Okay, now let's come to our example. Well, what you expect is, of course, that there should be norms on metrics on a real vector space which are not inducible via a norm on that space. Well, let's go back to what kind of metrics we know. Well, we can introduce something new, but this discrete metric in that case is very promising because it has very little structure. It lacks structure. So let's take R2. It's a real vector space. Let M be the discrete metric on R2. That is, you take 2 points in the plane. If they're equal, according to this metric, the distance is 0. If they're not equal, 1. That's what this metric is. Now let's suppose that there is a norm on R2 which induces this metric. Suppose there is some norm on R2. Well, let me give a symbol to that on R2 such that M is induced by this norm. Now we wish to show that this leads to a contradiction. But intuitively, this has to do something with the algebraic vector space structure here, because this metric carries no algebraic structure with itself. So it has to lead to contradiction either with vector addition on R2 or scalar multiplication on R2. Okay? This metric cannot carry that information. Now, the easier way is, well, they're both easy. You can do both ways. Now, let's consider the following. Take 0, 0, 1, 0, 2, 0. They're both in R2. Now let's consider the distance between these and between these, both of these from 0, 0. That's the easy, but according to M. Now, M of 0, 0, 1, 0. Well, this, by definition of the discrete metric, that's 1, because these are not the same. But by the supposition that this norm induces M, this will be equal to the norm of the difference 1, 0, 0, 0. But this is just the norm of 1, 0 when we perform this operation. Likewise, if we consider the image of this pair under M, now this on the one hand side will be equal to what? By definition of M, these are different, so that's 1. But this will be, since we assume that this induces M, it's 2, 0, minus 0, 0, and that's equal to just the norm of 2, 0. But here, as you see, the norm of 1, 0 and the norm of 2, 0 turned out to be the same, which cannot be the case since by N3, now 2, 0, this vector, is nothing but the scalar product of 2 with 1, 0. But by norm property 3, this is the absolute value of 2, that's 2. But this is not 2 times 1, that's 2, while this is 1, so a contradiction. As we expected, M is not induced by any norm on R2. In the sequel, we will do a lot about metric spaces. We will work mainly in metric spaces. But now we have to proceed in constructing a topological structure. That's what we'll start with in the next section. We'll define openness and closedness for subsets in a metric space, and then utilize them in formalizing what it means, given a point and a set, what it means for the point to be arbitrarily close to the set. But if I had given you a questionnaire which has the following picture, this set in R2, this set in R2, and this set in R2. Well, the dashed curve, that means points on the dashed curve are not in the set. And well, you were supposed to answer just according to your taste, well, which one of these sets is open, which is closed, and which is none. How would you mark this? Closed. How would you mark this? Open. And we would mark this neither open nor closed. Now, what's the intuition? How can we formalize that? Well, here, this contains its boundary, whatever that means, but pictorial, what the boundary is clear. This excludes it entirely, but this includes some part of the boundary and excludes some other part. Well, this will turn out to also be a characterization of openness and closedness and being none, but we will not take that as our defining condition, because that requires the definition of a boundary and so on. So that will come later on. Okay, now, another test will be the following. Well, this is all in the plane. Given a point in the set given, can I find a circle around that point? I can choose the radius as small as I wish, such that this circle is entirely contained. The interior of the circle is entirely contained in the set. But that for each point of the set. Now, in here, if I take this point, no matter how small a circle I choose around this, some part of that will lie outside. But here, no matter how close to the boundary you take a point, you can always find a small enough circle which is entirely contained. This pictorial description, that will actually be taken, that will be formalized and be taken as the definition of openness. Then we need the definition of a ball. That's what we'll start with next time, and then we'll introduce open and closed sets, and then we'll go one further step in our abstraction process. We'll find decisive properties that open sets satisfy, like the inner product satisfied, like the norm satisfied, like the distance satisfied, and we'll take those decisive properties to define what the topology is. But that will come next week, so I guess you will hand in the first week's homework.